Welcome everyone. We're just waiting for folks to join. So you can keep your video off and mics muted for now if you like, but we're gonna wait just a few minutes. Hi everyone. We're gonna wait about 2 more minutes just to see who else shows. So you're in the right place. Just hang in there. 5 minutes again. Okay. Hi everyone. Welcome back to our tutorial session. And today I wanted to share with you some pointers on moving forward using StatCrunch and some things that are going to come up in the homework. And I also want to give you an opportunity to ask me any questions, particularly if you're feeling confused. Even if you were able to answer the exercises, fine. You may have had some questions as to why answers were what they were. Overall, I'm super pleased with how everyone was doing with the homework and the quiz. I didn't see any major themes or areas where we need a lot of work as a group. Obviously, there's going to be individuals who are maybe struggling with certain concepts, but I want to go over a few concepts today before we open it up to other questions. And then hopefully this will help you make the leap from descriptive statistics to inferential statistics, which that's a big leap to make because we're all used to using statistics for things that are purely descriptive, things where if we go to a baseball game, there's going to be quote unquote statistics, which are batting averages and things like that. And those are statistics sort of because they're numbers and they're quantifiable, but we're not really trying to make inferences based on those numbers. And so the textbook now is making the leap, as are you in the homework, to going to inferential statistics, where we're taking samples and trying to say something about a larger population. And so that is kind of a hard concept to get our heads around. But if you think about it, statistics are often used as a tool to assist us in doing research where we only have access to a certain number of people from a population. So if we do a medical study, we may only have 100 patients from which we're trying to make a statement about a much broader population of patients. Now, ideally, if we're going to do something like a clinical trial on a drug, we will recruit thousands of patients in our study. And from that population, we will hopefully be able to say something about its effectiveness in the general population. And so it's used all the time, this inferential statistics, but it may be slightly less familiar to some of you who've never really done research. And in this era of big data, it's tempting to think, oh, well, we have information on everybody and everything. And it's really not the case, especially here in the United States, where healthcare systems are very fractured, meaning the data sources that are housed at one hospital aren't connected to another hospital. And though that's changing a little bit in terms of the amount of information that's available out there, we still never have the entire population. We never know everything about everyone. And that's a good thing, I think, from a privacy standpoint. There are other places like Scandinavia, which have a unified healthcare system. And so you can actually get entire population data on the population of Sweden. And you don't really need inferential statistics if you have everybody. But we're often trying to make assertions based on evidence that we can collect reasonably in a study. So that's the big difference. And if that concept is elusive, I understand why it's elusive. But that's kind of where we're headed, is using statistics more for the purposes of doing it in the context of research. Okay, so that said, one issue that did come up in the homework and on the exam is the concept of correlation. And a couple of things I'll say about correlation. One, you've probably heard the expression, correlation does not mean causation. And that's true. We also don't want to loosely use the term correlation to mean associated. And so I want to bring that up. In this course, and when we're talking in terms of statistics, correlation has a very specific meaning. It means when two interval or two continuous measures are correlated with one another in a linear fashion, and the extent to which they are linearly related to one another. So you can go back to using correlation loosely outside of this class, but correlation really means specifically for that situation where we have two interval level measures, which we are formally correlating. The default thing you can say, and this will always be accurate, would be to say an association between two variables. So the correlation is a type of association between two measures. But when we start looking at things like 2x2 tables, and we see an association, and as we get into chi-square tests, we will also talk about association. That's a universally okay term to use, association. But also conceptually with correlation, the coefficient that you've calculated already, the R correlation coefficient, it does not actually specify which of the two variables you're trying to predict, or one is not necessarily the dependent variable or the other an independent variable, or you're not saying that X causes Y. And conceptually, that's really important because when we calculate a correlation coefficient, it doesn't matter which we specify as the X or the Y variable. We can do them, select them in any order. Okay, so let me give you a quick example. And if I'm going too fast, or gosh, I hope my microphone's on. Otherwise, I've just been talking. I have some new data to look at, and this is, hopefully you can all see this. Can you see this? Can you nod if you can see the data? Thank you. Okay. So really, this is a very simple data set, and it's looking at the relationship between serotonin levels and aggression among chimps. I don't know if you know anything about primate species, but chimps are jerks. Let me just go out there and say that. Chimps, like, of all the primate species, they're just little brats. Bonobos are a little more gentle, a little more friendly, but yeah, so chimps, chimps are pretty aggressive little guys. And And so what we have here is a sample of 9 chimps. And we have the number of aggressive acts. So that's basically how many times did a chimp bite somebody, not somebody, another chimp. These are all chimp on chimp activities here. So we've got how many aggressive acts. That could have been hair pulling or whatever monkeys do, not monkeys, chimps do to each other. Okay, so the highest number of observed, and this is based in a laboratory setting, the highest number of aggressive acts per day was 6. And the lowest number was 2.2. So this chimp was relatively easygoing. This chimp was, you know, beating up other chimps. Okay, so that's the range we have for aggressive acts. Serotonin levels, the unit is unimportant, but basically higher is more serotonin. And if you don't know, serotonin is an important aspect in understanding mental health. It's also important in understanding aggression. It's actually an important factor in depression and schizophrenia and all kinds of things. So the reason we're looking at serotonin in this data set related to aggression is we actually want to be able to say something about humans ultimately, but this was a study done in animals. Okay, stay with me. So normally we would have a much larger sample, right? But often in laboratory settings, it's harder to get big samples, especially when we're using something like chimps. So this is a sample size of 9 chimps. But it's amazing how we can actually, from this very small group of subjects, start to see an association between 2 variables. So in the context of correlation, so here we have serotonin and we have aggressive acts. These other columns, I created different versions of the same variable. One is where I mean centered the variable, meaning I took the mean of the measure and subtracted it. And I also created z-scores. So for now, I'm just going to ignore all the rest of this information. This is just here so that I can demonstrate some things with correlation. But here we have serotonin and aggression. So if I were to want to just kind of understand what's going on in my data, I might start off by doing a scatter plot, right? We have 2 continuous measures, so scatter plot is the way to go. So we've got, I'm going to put serotonin as my X and aggressive acts as my dependent, okay? But again, for correlation, it doesn't matter. But conceptually, you could argue that since we're interested in the effect of serotonin on aggression, we should put aggressive acts as the Y variable and serotonin as the X. And this will come up more when we do linear regression, where we're actually formally stating what our dependent variable is and what our independent variable is. But for correlation purposes, it doesn't matter which order we put them in. So I'm going to go ahead and compute. Oh, it's going to hide right behind here. Okay. And scatter plots are useful when we have small data sets. If we had a really large data set, it might be hard to visualize any kind of pattern in the data. But you'll see here, the chimp that had the lowest serotonin level was also the most aggressive, with 6 aggressive acts. And the chimp that had the highest serotonin had the lowest aggression down here too, okay? So on here, serotonin level, as serotonin level increases, overall, we can kind of see a general trend towards lower aggression. So that's kind of nifty, interesting. Okay, maybe serotonin affects our mood or at least our behavior in some way, or I shouldn't say us, chimps, okay? But before I can really jump, so this would be a first step. I'm looking at the data. Some of you struggled a little bit with plotting a line, and it's a little confusing in StatCrunch because there's not a default line, okay? Right, a scatter plot just plots the point. So if I want a line, I'm going to do scatter plot. I'm still gonna keep the same aggressive X. And this might not have been obvious to some of you. Somehow you all figured it out. You must have been watching the tutorials, which I appreciate. But if I do polynomial order of 1, I can get here the best fit line. That would be the normal thing, that would be the most typical thing to do when you do a scatter plot. Sometimes we try to fit non-linear lines to data, but often when we're doing a scatter plot, this is what we're hoping to do. So, so I hit compute. Okay, now we get our best fitting line. And conceptually here, what we want to think about is, first of all, does the relationship truly look linear? Because if it had a U shape or something else, it wouldn't even be appropriate to report out a correlation coefficient. Correlation is assuming that there's some sort of linear relationship. Okay, so yes, there might be some slight variation from linearity here that would fit better. But especially as we get towards regression, you'll see that we tend to simplify things just a little bit. And so even though this might not be perfectly linear, it's linear enough, we all say. And you can see here from this best fitting line, how much each point deviates from this best fit, okay? So if I'm just trying to understand, am I getting a signal here? Is there an association here? It does look like it, right? I mean, it looks, especially with the highest aggression, with the lowest serotonin, and the lowest aggression with the highest serotonin, and there's the other points aren't cooperating perfectly, but you can see that there's an overall pattern. Okay, so we're getting really excited. We're like, oh, we're going to publish our paper that there's a relationship between serotonin and aggression, and this is going to be awesome because we found this association. Well, if we were to do a formal test of this, well, first of all, let's calculate. Let's not even do a formal test. Let's just look at what the correlation coefficient is. Okay, it looks fairly strong, but how strong is it? So I'm going to go ahead and get rid of that, and I'm going to do summary stats, correlation, and I'm going to do serotonin, serotonin and aggressive X, and then compute an actual correlation coefficient between these two measures. Okay, and you can see here that the correlation is negative 0.636. Does anybody want to take a shot at interpreting that correlation coefficient of negative 0.636 in terms of its directionality and its strength? You can just shout it out. Anybody?
I want to see the linear graph will be decreasing. It will be going down instead of going straight.
Oh, it's going down.
It will be approaching. It will be approaching zero. Because
okay,
it is a negative correlation.
Yes. So a negative correlation. So 0 means there's no correlation. A negative number close to -1 would mean the -1 would be a perfectly inverse relationship. As one variable goes up, the other one goes down. A positive correlation would be 1 point 0. That would be a perfect positive correlation. And that means as the other one variable is going up, the other is going up proportionately. And so a negative 0.636, don't forget 0 is what means no correlation. Negative does not mean less than a correlation. Actually, this is a fairly strong, moderate to strong negative correlation, which is just as strong as if this was a positive 0.36. It just so happens that the relationship is inverse as opposed to positive. So that is a little confusing in itself because we tend to think of higher being stronger, but really the reference point is 0 and the maximum is +1 and -1 for a correlation. Okay. So what's nice, okay. I'm sorry, did you have a follow-up? I can't see.
Say that one more time, Professor.
Can you say it a little louder? I'm sorry. Okay, I couldn't even see who was talking. That's okay. If it comes up again, we'll chat about it. So that's something important to consider. The correlation coefficient is a unitless measure. It's not like it's -0.3 aggressive acts. It's not like it's -0.63 units of serotonin. It just is the correlation coefficient. It's a unitless thing, and it's because it's actually based on standardized versions of the variable. And by standardized versions of the variable, you calculated those previously where you first subtracted to the mean subtracted the mean from the original value and then divided it by the standard deviation. So a standardized variable expresses how much a measure is deviating from the mean of the population. So a positive value would mean that they're well above the mean or how far they are above the mean. A negative value would be that they're below the mean. And it's actually fairly useful. Here I calculated, first of all, as a preliminary step, I just did centered version. So this is simply the original values minus the mean. Now you don't normally do this when you're running analysis. I'm just doing this for demonstration purposes. So here are my z-score versions. These are the ones where I've standardized the measures, right? Because the reason we do this is serotonin is measured on some sort of micro units of serotonin. I'm not actually sure what the biological measurement is of serotonin. I should look that up. But it's some measure. You can see what the range is here. It goes from 0.35 to 0.63, which is a very different type of unit than an act of aggression, which the lowest was 2.2 and the highest the 6. These are really just completely different types of measurements. But what's nice about the correlation coefficient is that we can use this across all kinds of measures, because when we standardize it, we're making it so that it's in terms of its own standard deviation. How much is it deviating from its own mean? And if I just kind of look at these numbers here, this chimp that was really high on aggression, I'm sorry, really high on serotonin, was pretty low on, I'm sorry, high on serotonin, low on aggression. So you can see a positive number here and a negative z-score for aggression for this extreme example. And if I go to the other extreme, which was chimp, this chimp that had very low serotonin, their z-score was -1.29 on serotonin and +1.29 on aggression. Okay, and it actually is a useful thing to look at because it helps us get our heads a little more about where they sit with respect to their means. You can also see this with the centered versions. But notice if I do a correlation, summary statistics correlation on the z-scores, I'm going to get the exact same answer, negative 0.636574. Okay, so by computing these z-score versions of the variable, I didn't fundamentally change the variable. The variation in that variable is exactly the same as the original variable. It's just expressing it in slightly different units. If this is confusing, that's okay. But I just wanted to show you what a correlation coefficient means, because it's slightly different than when we get to linear regression later, where we're actually talking about unit changes in one thing and how much that affects the outcome in original units of the variable. In the context of correlation coefficients, these are unitless measures that tell us the relative strength. So that's why we can make these general rules of thumb that negative 0.4 is a, I'm sorry, 0.4 is a moderate correlation, moderate positive, or weak positive would start at about, 0.3 to 0.5, moderate 0.5 to 0.7. There's different rules. And as if we get to like 0.8, 0.9, then we have a really strong correlation. And it doesn't matter what types of variables we use. We can use, well, I'm sorry, it doesn't matter what the original units were, as long as they're either interval or continuous measures, we can run correlations. Okay, so I wanted to make those 2 points clear. One is that it's unitless. The other is that it does not imply causation, even if we may have a hypothesis suggesting there's a directionality to the relationship. In theory, maybe the aggression changes the chimp serotonin levels. It's biologically plausible. Maybe they, maybe after they act aggressively, they, so we wouldn't be able to prove causality even based on this. Okay, so one last final step. I did not actually do a formal statistical test. Now this is jumping ahead a little bit because we haven't yet run statistical tests on correlations, but you can do that. So if I do stat summary correlation, I can do a two-sided p-value and compute. And it's a little awkward in the output because it doesn't label it. But the first value here is the correlation. And this is the p-value, 0.065. So after all that excitement about the relationship between serotonin and aggression, turns out, based on the standard p-value of 0.05 being the cut point for something statistically significant, this is actually not a statistically significant relationship. That stinks. Can't publish our results. Okay, but it was kind of exciting for a minute there. I thought we had this, breakthrough in understanding behavior. Can anyone explain why this wasn't statistically significant, even though it looked like a fairly strong correlation? Or any guesses? Any guesses? Why, even though it looked like a fairly strong correlation?
Is it, Dr. Good, is it because there was no like formal correlation? Because we had one end, it was just the negative factor of it, and then from another stand, it was a positive. So there was no actual formal correlation to it.
So no, so actually, no, we did have a fairly, or the appearance of a fairly strong, a negative correlation is just as good as a positive correlation. So even though it was negative,
Together.
just as good.
Okay.
Yeah.
Yeah, okay.
What do you notice? Maybe I'll give a hint. Look at the data. Just look at it. What do you notice about it? You don't even have to look at the numbers. You can actually just like gestalt look at this table? Any guesses? Okay, well, I will tell you. This is a really small sample, right? This is a tiny sample. And then we're doing a study of humans. 9 would be unacceptably small. Like, you only recruited 9 people to your study? Epic fail. But I mean, in the case of laboratory studies, we might only have access to these kinds of numbers. And so we're kind of stuck with these traditional notions of statistical significance. But if you didn't get that, I was just seeing if you understood the relationship. So even though this was not statistically significant, I would not give up on the plausibility of this relationship between serotonin and aggressive acts. And the way I would go about pursuing this, let's say this was purely exploratory, I would say, okay, based on this, there wasn't enough evidence to show a relationship. I still might want to report it in the scientific literature because it's interesting, but then I would design another study with a bigger sample and maybe, you know, measure things at multiple time points. That would increase what we call the power of the study. And then we could, okay. So that's kind of an advanced concept. I just wanted to see if anybody would pick up on that, because a lot of the statistics that we use are based on small samples, but not this small. So usually like a t-test will be based on 20 people per group, something like that, minimum. Could be smaller than that. But you know, if you're thinking about like psychology research or something like that, we want to try to get at least, you know, 15 to 20 people per group before we would apply statistical tests to it. Okay. So that was some stuff I wanted to share on correlation as we move forward. Correlation is a really important concept because it is the foundation of linear regression. And just to jump ahead a little bit, because this course only lasts 4 weeks, so foreshadowing here, just a couple weeks ahead here. But when we get to linear regression, I'm going to select your simple linear regression. It's going to very similarly ask me for what is my X variable and my Y variable. Here, we're going to be very explicit about what is our dependent variable, aggressive acts, and my independent variable, serotonin. Okay. And the difference, as you'll see, I'm going to run the output. This is jumping ahead a little bit. But the difference is in linear regression, I don't get a correlation coefficient. I get a slope. And a slope is actually in the original units of the variables. It's saying that as serotonin goes up a full point on the serotonin scale, aggression will decrease by 7, which is actually beyond the range of the data. Most any chimp actually was aggressive with 6. So when we get to linear regression, the slope is actually in the original units. But if I were to do a regression on the z-scores, simple linear, serotonin predicting aggression. Okay, look at my slope, negative 0.372. Looks really familiar, right? So if I were to run a regression on the z-score versions of these variables, it would be the same as the correlation coefficient. That's weird, right? Well, it's actually, because I've standardized units, basically what this means is a 1 standard deviation change in serotonin will result in a negative 0.37 standard deviation change in aggressive acts. So the interpretation here switches from original units to standardized units. Again, if you're confused by that, I understand, but that conceptually, correlation coefficients, you could think of it as the slope of the linear relationship between two standardized variables. But that's jumping ahead. But you guys seem to be pretty on top of things, so I wanted to point that out as we move forward, the relationship between correlation and regression. Okay, now that I've moved forward a little bit, let's get back to some questions that maybe you have. Anybody have any questions that have come up? I think it could be conceptual questions or specific questions. Do folks know how to use the raise hand feature? We should have a little, or you can speak up, either one.
Professor, can you go over the correlation, how that's a foundation for linear regression? Can you go a little bit more into
Yeah, sure. So conceptually, right now, what we're looking at is a correlation could be thought of as just a descriptive statistic, right? I happen to run a quick little statistical test to see if that correlation was statistically significant. But in general, we could just use a correlation coefficient as a description of the relationship between two variables. And in the context of correlation, we're really just saying, is there an association? Does it seem like the two variables are related? And what is the nature of that relationship? Is it positive, meaning are they going in the same direction? Is it negative, meaning they're going in opposite directions? And so the correlation coefficient is useful simply for descriptive statistics. We're not trying to really say much more about the relationship. When we get to linear regression, we are actually making a claim that there is a directional relationship between our dependent variable and either one independent variable or a series of independent variables. So a simple linear regression is really not any more informative than a correlation coefficient because it's still between two variables. It's bivariate. The reason why linear regression is more powerful is that we can then move on to add additional independent variables and look at the relationship between multiple variables simultaneously and an outcome. And this is when we start to get into predictive statistical modeling, where we're saying, okay, what are the factors that are associated with aggression? And let's say in this study, I also collected sex. So I know whether it's a male or female chimp. And I also collected the age of the chimp. And I also selected how many, their BMI or something like that, okay? Ideally, I would want to look at those other factors too, because it could be that nothing to do with serotonin. Maybe this is actually has to do with the sex of the chimp. And it happens that sex is also associated with serotonin. I would be able to determine that once we get to linear regression, because we can start to look at multiple variables simultaneously. But for purely descriptive purposes, if I just want to understand the relationship between two variables, which is what we're doing right now with bivariate analysis, and we can use this as just a general descriptive tool. I hope that's being clear. I am definitely jumping ahead a little bit because I want to make sure that I made the connection between correlation and regression.
Yeah, that clarified it. Thank you.
And really, as far as we're going to get in this class is linear regression. So we've already started talking about the most complicated thing we're going to do in this class, which is linear regression. But you will start to see a connection among all the different things that we're doing here when we get to ANOVA. ANOVA is actually related to regression as well. But the point is that we always want to pick a statistical test that is appropriate for the type or the level of measurement that we're using, right? So we wouldn't create a contingency table on serotonin and aggressive acts, right? Because these are continuous measures. It wouldn't make sense to do a 2x2 table. Now, we could, if we really wanted to use a contingency table, we could classify some of these chimps as being high on serotonin and some of them as being low on serotonin. And we could classify some as like aggressive and some not aggressive using some sort of cut point. Okay, so I could do that really quickly here. I could say that, especially since it's already sorted, I could say that if you're above 0.4, well, maybe I won't do that. But yeah, I'll just say above 0.4, you are considered high on serotonin. And by high, I don't mean high in value. Okay, and then I'm going to create another variable, which is high in aggression. And I'm going to say, I'm just making this up, more than 4 acts of aggression is you're aggressive. Okay. So all I did was I took the aggressive chimps, and if they were higher than a 4, I gave them a 1 here for my new variable, which is aggressive. And this is my measure of high serotonin. Okay. So if I really wanted to, I could classify these chimps this way and run a 2x2 table. Does anybody notice what happened here though when I did that, when I collapsed it into a dichotomous measure, yes, no, or 1, 0? First of all, let me just say, was this a good idea to dichotomize this? Well, let's see what happens when I try to run a contingency table on this, okay? So I'm going to do contingency table with data. And I'm going to say my row variable is aggressive and my column value is, oh wait, no. I'm going to say my row value is high serotonin and I'm going to hit compute. Well, I'm super stuck now because I have a 1 in one cell, a 1 in the other cell, a 2 and a 5. So I got really sparse data here. I thought I had a problem with running a correlation coefficient. If I'm going to do dichotomous variables, I've got very little to work with here. And so this was also underpowered to detect any kind of difference. In fact, it's even more underpowered now that I lost information from those original variables. By dichotomizing these 2 measures, I simplified and I decreased the amount of variance there. And now I even have less power than I did before. So if we do have things that are measured and quantified, generally speaking, we're better off using the original continuous measure than collapsing them into categories, because we ultimately have more statistical power for continuous measures than we do categorical. Okay? But again, we want to apply the right tool for the job. So in this case, I just arbitrarily made up these categories, and it wasn't a good idea. Nor were there any categories that would have helped here, because no matter what the cut point was, it was going to be far too sparse. Okay, but we really let the nature of the data or the nature of the study design dictate what we do as far as statistical methods. So the reason we have all these different options as we're looking through here, it's not just so that we can, use a hammer one time and use a screwdriver another time just for fun. Like, there's a very specific reason why we use the tools that we're using. And for descriptive purposes or just exploration purposes, it's fine to kind of just use some of these other procedures to kind of get your head around what's happening. You can even do a scatter plot of a dichotomous measure versus continuous measure. I don't recommend doing that, but like in theory, you could look at that. You just wouldn't want to report it out, but you're welcome to always use the tools to help yourself understand the data. Okay, one other thing I wanted to show you is in your homework, on the fellows' mental health data. Okay, one thing is a little, so this data is in your homework too. And it asks you at one point to run a t-test comparing married versus divorced people on their mental health scores. StatCrunch is a little clunky at doing t-tests. And by clunky, I mean it requires that you do another data step before you actually run a t-test. This is not typical in most stat software. So I just want to make sure that you all know how to do this. So notice that in all the data that we've looked at so far, the chimp data, this data, we have one observation per participant in the study. Okay. And that's normally how we set up our data. But to run a t-test, I actually have to, well, let me show you the t-stat interface for two sample. The first several questions is about one sample t-test where you have some reference value. But when we do a two sample t-test with data, it's going to say, give me the values for sample 1 and the values for sample 2. This is assuming that we have set up our data where we have the values for one group that we've defined, so married versus not married, in separate columns, which is kind of unique to the software. Normally we just tell it which variable we want to divide it by. So especially if you've used other stats software, this might not be that intuitive. So what you need to do for the two sample t-test, and this is the only time you ever have to do this in this course, I do believe, is you're going to have to go to data, arrange, split, and then you're going to select your column. We're going to do their mental health score, split by marital status. And then I'm going to hit compute. This is kind of goofy that we have to do this, okay? And what it does is creates separate columns for our divorced group and our married group and our never married. You could almost think of this as being a separate data set over here to the right, because you'll notice I only have 44 observations of divorce. I have 44 observations of married, and then I have 62 observations of never married. So this is a pretty awkward way to store data, but this is what you actually have to do before you run the t-test. So now I go in and I say two sample t-test. Oops. Sorry, t-stats, two sample with data. Okay, so now I'll just say divorced versus married mental health. Okay. And now I can hit compute and I will get the results of my two sample t-test. So mechanically, that's what you have to do to set up a t-test. I think the reason why StatCrunch does that is because conceptually, these should be two independent samples that we're testing. And so we're basically creating a little data set that has a sample of married people and a sample of divorced people. And we're going to run them side by side. In other stats programs, we're going to say, hey, just use the marriage variable as an indicator. But this is how we have to do it in this one. Everything else we do, ANOVA, linear regression, everything else, you don't have to do any data transformations before getting it to behave. But in this case, just for the two sample t-test, you have to set it up that way. So just keep that in mind. I didn't expect that when I used the software. I hit a roadblock there because usually I would just select the variable that I wanted to use as a factor variable. And in fact, when you get to ANOVA, which is really kind of an expansion upon a t-test, you don't have to do any data transformation. So let me show you an example. So for ANOVA, all I'm going to do is say ANOVA one way, give it my column variable, mental health, and my factor variable is marital status, and hit compute. And now it has divorced, married, never married. And so I didn't have to do any data transformation. I didn't even use these new variables for the ANOVA. So it's really just for this t-test that it's a little bit clunky. So I just wanted to warn you about that. Okay. Other questions? If anything I said tonight was confusing, it may make more sense later as you move through the materials. So you may want to come back and look at this video then. But I was trying to move us forward rather than stay back where we were, but mostly because I was really impressed with how much you guys seem to be grasping these things. But I am so happy to go back and look at other things that you need clarification on. So ask away.
Excuse me?
Go ahead.
Oh yeah, I didn't know if you could hear me. I just had a question. This was being recorded, this lecture is being recorded. Will it be like posted for us to go back and rewatch?
Yeah, it'll be posted. Last time it was that Thursday was my birthday, so I didn't post it until the evening. I will do it first thing in the morning this time.
Got it. Thank you.
But yeah, I will be more on top of it. I wasn't looking for birthday wishes, by the way. I just want to explain why I didn't show up until like 8 o'clock.
Happy late birthday, by the way.
Oh, happy belated birthday.
Thank you. All right. Other questions?
Yeah, Professor, I have a question on question 12.
For assignment 2?
On question 12, week 2.
Okay. Go ahead. What's your question?
I was wondering if we were going to use the alpha value to look for another t value to compare it with the one that has been given. Is that the way we're going to go about the question?
Okay, so the question is, so this is homework assignment 2. And the question is, for each of the following t values, indicate whether the t statistic is statistically significant for a two-tailed test at the specified alphas. So yes, you will look at the table of critical values that's available in your textbook and determine if the value exceeds that threshold or is below that threshold, and therefore would be statistically significant or not. So yes, you are going to use the value of t values for that. So normally when we use statistical software, it's just going to present a p-value for us when we ask it to. But for this particular exercise, it's for those t values, you're going to look it up in the table.
So I'm going to look it up in the table and graph it and compare it with the one that has been given, like for question A. The first t that is given is 2.90. So I'm going to use the alpha value, that's the area, to compute another t value and then compare the two and see where they fall. If they fall within the range or out of the range. Is that the sort of thing that you are expecting?
Yeah, so let me make sure I'm answering this correctly. Okay, I guess I'm a little unclear on the question. Can I follow up by email with you? Because I'm not sure if I'm understanding the question.
Okay, Professor, I'll send you an email.
Okay, I'll follow up by email with you.
Okay.
Okay. Any other questions? Okay, well, just know that as we move into this next section on inferential statistics, it is going to take a kind of leap of thinking about what it is we're actually doing with these statistics. And we are trying to look at unknown parameters that we're trying to estimate using our data. And so when we're creating things like confidence intervals, we're saying, okay, well, this is what we calculate. And this is what we observe as the difference between two means within our sample. Where does the true population difference likely sit based on our sample? Where does the true population mean sit relative to our sample? So when we compute confidence intervals or compute differences, we have a confidence interval around a difference. It's because what we're doing is based on a relatively small number of observations compared to the whole. And so just by chance alone, we could have had slight variations in where the difference is. I'm sorry, we could have just slight differences in what our sample means are. And therefore we could also have differences in what our differences are. And so we develop confidence intervals around those. So if I were to randomly sample, 20 people on the street and took their height, I might get actually close to the average of the population. I'm in Seattle. So if I took 20 people purely randomly, I might be kind of close, right? I mean, not going to be too far off from the average. But if I were to do 2,000 people, take me some time, but if I did it, I would have a pretty darn good measure of what the average person in Seattle's height is, right? If I took 200, and it would get even better if I did 2,000 or if I did 20,000. So as we get bigger and bigger samples, our estimates become more reliable. And you'll notice that our confidence intervals get narrower, not wider. They get narrower as our sample size gets bigger because we are using more information and we get closer and closer to the true population. If I really wanted to do it, then I would include it in the census and have the census takers take everybody's height, but they don't do that. So we have to use samples to determine those things. Okay, well, I'm gonna, since it's 7 o'clock, I am gonna cut us off here. However, if you have individual questions, I will be happy to answer them either by email or in separate office hours. I will add to the end of this video my answer to the problem on question 12. I need to spend a little more time with it myself before I give, without giving away the answer. So I will include that in the video before tomorrow. And I'll also send out an email clarifying what's expected in question 12. Okay. All right, well, thank you, everyone. Professor. Have a good night.
Professor, I sent
Yes.
you in the chat.
I'm sorry?
I sent you something in the chat if you were available.
Oh, I'm so sorry.
Yeah, that's fine.
Okay, sure. Rosie, you want to hang out for a bit?
Yeah, please. Thank you.
Sure. I'm going to go over just some stats crunch up. So you're welcome to stay on, but Rosie's going to lead away. So, all right. Go ahead, Rosie. What kind of help do you need?
I just was having some trouble with the assignment for StatCrunch wasn't really because I did go through your videos, but I just didn't. I was having problems with the assignment.
Sure. Okay. So let me.
That's why I said maybe I need to go to see you for office hours.
Yeah, but here let me just stop share. Oh gosh. It's not liking that all of a sudden. Oops. Okay. So in general, first of all, Rosie and everyone, can you see my screen? The StatCrunch screen?
Yeah, we can see it.
Yes, you can see it.
So what I just showed you in the examples is more like a data set and running analysis on data set. A lot of the homework, you're going to actually enter the values into StatCrunch. So if you have values in a problem set and yours to calculate the mean, I'm just throwing in some numbers here. Okay, let's say I'm doing average depression score. Okay, so I'm typing in the values. So you're actually going to almost use. Yep. This. Yep. Go ahead. Okay. So you're going to use StatCrunch more like a calculator. And so if there are ever less than like 20 observations, you're just going to put the numbers into StatCrunch. And then let's say I want to calculate the mean on this variable. I can go here and do summary stats, columns. Here I didn't even give it a name. But here I can get things like the n, the mean, the variance, the standard deviation, etc. So for a lot of the early questions in homework 1, for example, you're actually going to manually enter the data, and then
Oh, that makes so much sense because
okay, good.
for for problem 5, I just copied and pasted, and I don't
Yeah.
think like that it didn't make any sense because what the answers that I was getting, it was like 40 people, like 40 occurrences of like someone falling, and I had to type in like the numbers that came up, and it just didn't make sense for what I was getting
Right.
for
Okay, yeah.
yeah.
So you would just
With the frequency distribution table. I just didn't understand like what I was getting.
okay.
Mhm.
Okay. So, and generally if it's more than 20 observations, it'll ask you to import a data set. So for example, the data that I just used, I actually got from on my computer, the fellows mental health data, open that from Excel. And it's all in there for me, okay? So if it's relatively few cases, you're gonna manually enter it. Otherwise, we'll provide a data set for you.
Mhm.
That's clear. So Rosie, are there other questions that you were having?
For the homework, let's say if we don't input the data like properly, will we get any points or like
Oh
it's
yeah,
just
I mean,
completely
usually I'll be able
wrong?
to tell that. Like that happened a couple times in the first homework. I noticed that there was one, yes, absolutely. If I can tell that it was just a simple entry error or something like that, then absolutely yes, I will give you partial credit
Okay, and
or full credit depending on what the situation was.
all right, because I think that's gonna be a problem of mine. I don't know, like I'm more of a like vocabulary I get really all the time, but just like inputting in statistics, like it's kind of difficult for me. Like I don't really understand it too much. So
Sure. Well, and if you suspect that you may have been in error, you could put a little note in the Word document just saying, hey, I think this is right, and can you check it or something like that. And I can also look at homework before you formally submit it. If you just want to run it by me, if you send an email with an attachment, I can take a look at it.
all right, thank you. Yeah, that's all I have for today. Again, thank you so much.
Awesome.
Thank you.
Were there other questions that I can answer now? Okay. So feel free, I think with a couple of you, I have appointments tomorrow, so I'll see you then.
Yeah, I was gonna just mention, I have several questions, but I'll definitely review that with you tomorrow, Professor.
Okay, sounds good. See you tomorrow, Ruby.
Professor, could I like actually make an appointment as well? Because I'm from the East Coast, so like the hours are completely different. It's just I would want to make like an appointment to check my work or to
Sure,
see if, I'm doing stuff properly.
sure. What time works well? This is Rosie, right? I'm having trouble.
Yeah, this is Rosie.
You're on the East Coast, you said?
Yeah, I'm in New York.
All right. So what about would 3 o'clock your time work?
3 o'clock for you or 3 o'clock for me?
For you, noon my time.
Yeah. Okay. So that'd be early for you. Okay.
Is that fine?
It's for tomorrow, right?
Yeah.
Okay. It's just like in a Zoom call, we can't just go over like the assignment, right? I just ask a question.
In the Zoom call, we can go over questions.
Like I this is my first statistics class and I'm doing it for my nursing program and I'm just like it fit my schedule, but I feel like it's a lot more advanced than I could
Okay.
deal with. Like I need, I
Sure.
don't
Well, I'm
know,
happy to walk through. Is there a
resources.
specific question I can help with?
Just yeah, I was having a problem with stat crunch, really, not anything else.
Okay.
And I'm kind of behind with the assignments because I was a day late. Like the class started I don't know, the 6th or something, and I like got enrolled the 8th.
Oh,
So
okay. Yeah, no
yeah, I'm
worries.
kind of behind because of that too.
Okay, I didn't realize that. Oh, so you're one of the, yeah, I just have 2 late ads. So if you're one of those, yeah, I'm
Yeah.
totally willing to work with you on that one. No, this was a
Thank
fun
you so much.
quarter anyway, or quarter, 4 weeks because we started a day late. So yeah, no worries.
Because this is class that I've ever taken. So it's,
Yeah.
and I'm not good at math, and I'm really trying my hardest to like, because it's a prereq for my nursing program.
Yeah, no, I get it. So let's set up a time to go through, but I'm happy to answer. I'm here now, so if you have a specific question, I can help you.
It was just for that problem. I'm just trying to, I got a 19 out of 20 for the quiz.
Good.
And yeah, and I just need to do the discussion post and this assignment. And I'm
So
gonna,
assignment 1, is it assignment 1 we're talking
it's
about?
assignment 1, yeah, and I'm gonna
Okay.
try to do assignment 2 by the due date, which is the 17th.
Okay, yeah. So let me go back to, unfortunately I have to log in again here.
Hmm.
Booted me out. Okay, I'm gonna share my screen here in a second.
Mhm.
Okay. All right, so let's go to week 1. So we're talking about the main
Week 1
assignment, right?
assignment, yes. Mhm.
Okay. All right. So you tell me, first of all, you can still see my Word document here, I assume?
I don't see the Word document. I just see the Blackboard.
Okay,
Oh.
let me get it to share that.
Mhm.
Oh gosh, I hate when it does that. Here we go. Yeah, okay. Now can you see the Word document?
Mhm.
Okay, awesome. So, yeah, I'm guessing you don't need help with the first one.
No, I don't need help with any of the like.
Okay.
No, just
Okay, so starting
number 5.
here,
Yeah, when we.
So this one, yeah, you would actually enter all these values into StatCrunch.
StatCrunch, okay.
Yeah, and
I copied, like I told you, I copied and pasted it. But then after that, I put in StatCrunch and I couldn't do, I did the frequency distribution, but it kept doing them separately, like each like column.
oh, right, okay.
Yeah, and I
Right,
just
so
couldn't
this
get
would,
why I was
let me
doing
show
that.
you what this would look like in StatCrunch. So I'm gonna have to switch gears here. I could do both at once. Okay. So I'll assume that you have that document open or you remember what this looks like. I'm gonna do a new share here.
I have it with me right now because like
okay,
I've been
great.
trying to do it. So
Yeah. Oh gosh, did I close it down? Oh. Must have shut it down 1 second. Sorry.
and professor, not to get ahead of myself, but for the project, it's gonna be kind of the same, like these types of questions and like
Sure, no worries.
putting in.
Yeah, I have just trying to find the. Second. Here we go. Okay. So, so as I was mentioning, So really, StatCrunch is kind of like Excel, right? It's just like a glorified version of Excel. So I'm gonna enter in those exact numbers, those observations, and so it's a little tedious. I'm gonna go 3, 3, 4. This is probably the most data you'll have to enter. 1, 1, 2, 1, 1, 2, 0.
Oh, so all of that in one row.
Yeah, all in one column. Yeah.
Oh,
Yeah, I know that's not that
okay.
clear. Sorry, you struggled with that because
No, it's all right. I was just
no,
like, what am I doing wrong?
no, I get it.
Mhm.
So I'm entering all that in. Yeah, let me just do that real quick.
Mm.
Yeah.
Okay. And that's for all of the questions?
Well, and so like I said, I think this is the part of most you're gonna have to enter.
Until
It's a little bit. Oh, oh gosh, and back in the old days, we would do this all by hand.
no, I'd rather do it right
So this
and then
is
it'd be tedious
the
than
phase
like
that
do it
I'm
wrong
going
and then
to do.
not getting the points.
One. I'm almost done. 0, 4,
Mhm.
6, 9, 0, 1. Okay. So yeah, so this is all now in one column, and now it's asking me to construct a frequency distribution table, show the absolute frequencies, etc. So I am going to
Tables, frequency.
tables, do frequency,
Mhm.
and I didn't even give it a name, but here it is, var1. And here I can select, I can hit control frequency, control relative frequency, cumulative relative frequency, and then hit compute, and it'll give me
Oh my God, really?
frequencies,
That was okay.
the relative frequencies, the cumulative relative frequencies. And then, so is
That's a
that
lot better
clear
than
so
the
far?
tables that I got. So yeah, it makes sense now.
Rosie?
Yeah, you hear me? Hello? Hello?
Hi, Rosie.
Yeah, you hear me?
Oh, sorry, were you talking?
Yeah, I was. Do you hear me? No, I don't.
Sorry,
Hello?
Rosie, might somehow accidentally hit the mute button on my end. I'm so sorry. So is this clear?
Yeah, it's clear. You hear me though, right?
Yeah, now I do.
Okay. I got scared. It's clear now. Yeah, I got that question, and then it's just I'd have to manually put in everything, basically.
Well, up for now. Yeah.
For now, okay.
Yeah.
Okay,
So
no, I just want to get it like the points. You know, I don't want to like just do it and then get everything wrong and like not get the credit. So now,
yeah, so likewise, number 9, you're gonna input that one column, all those numbers, 41, 27, 32, 24, 21, 28, 22. Very good.
but what about like number 15? Can I just copy and paste that or no?
Let's see, number 15. Oh, yes, you could. Yeah, you could. Because it's already set up in columns.
Oh, all right.
Yeah. Although, yeah, you could. So you could just, let me show you what that would look like. I'm gonna go into the Word, copy it, and see. So hopefully you're seeing my StatCrunch screen here. I'm gonna get rid of my old data here, a little messy. And I literally just in the Word document, and then oh, that didn't work. Wait a second. Oh, there it is. Okay. I don't know why I did it down there. That was weird. Oh.
So yeah, it did. Okay, that's good.
Yeah.
So
So if you ever have issues with doing something like that, you could also just do it like column by column in case it like screws up. But yeah, hopefully that works.
all right. And each problem, do I have to make a new like tab or something? Do I just
Yeah,
have
that
to-
would probably be the cleanest thing to do. You could just do, you could do, new data table under the stat crunch tab. You can just do new data table and it'll
make another one?
make another one.
Okay, perfect.
Yeah.
No, I'm getting the hang of it. Okay.
Yeah, it's funny because we're kind of using stat crunch both as a calculator and as an actual like where we have a data set. And so the first few exercises have you manually enter. As we go forward, you're going to be importing more from Excel. But I mean, in reality, you could also just take an Excel data set, copy the whole thing and paste it into here as well. So you don't have to.
Yeah, I'm not gonna do that because I'm just gonna confuse myself more than I already am. Kind of
Don't
confused.
do that. I'll just, yeah,
Mm-hmm.
whatever you have to do to get it in there.
Yeah. Okay. Thank you so much, Professor. After, I'm just gonna try to get on the assignments, and I'll send you an email if I'm gonna be like behind an assignment too. But I
Okay,
think
that's fine.
by
I'm
tomorrow.
totally flexible on that. Do you still want to schedule something for tomorrow, or are you gonna?
I'm gonna try to do assignment 1
Okay.
by tomorrow, or just try to get both of them in. But like with the assignments, like I said, Professor, I've never had like a statistics class, and like I'm really bad at math. So if I'm behind with the assignments, I'm really start. But the quizzes, I'm never gonna, like you said, there's no like excuse on the quiz. Like we have to get it in by, I think, Sunday 11:59, and then yeah, with the quizzes I'm gonna be good. But with the assignments and discussion posts, I'm kind of like
That's
a
fine.
little slow with that.
That's fine. That's totally
Okay.
fine. Yeah.
Mhm.
Right. Yeah. It's just, I mean, there's a fairness issue with the quiz as far as allowing people to do that different times, but the homework, I just really want you to get through it. So as long as you're keeping pace and you're giving me feedback and you're letting me know what's going on, I'm totally fine with that. So
I
don't.
think the only problem I'm gonna have is just like doing the assignments, because reading the text and doing well in the quizzes is pretty good for me. Like I'm just, but
Mhm.
just all putting in all the stuff in StatCrunch, and
Yeah.
the data part is gonna be hard for me. So
And it is pretty time consuming, especially when you're entering data. So
yeah.
yeah, no worries. Just keep in touch with me on it. And so yeah, as long as students communicate what's going on and are working towards getting it in, that's all I ask. So
Okay. Thank you, Professor.
sure. Thanks, Rosie.
Okay. Have a
Let me
good
know if
day,
you-
or for me, it's a good night.
Yeah, same here.
Okay. Good night. Bye.